Welcome and thank you for joining today's AVS e-talk on the surface microscopy and microanalysis in an industrial research laboratory. This will be presented by Vincent Smentkowski, Senior Scientist at GE Vernova Advanced Research Center. I'm going to go through some informational slides before we have Vin share his screen. When you logged in today, you are automatically muted. Be sure your volume is up and that your screen is in full view. This is a 1-hour presentation with no scheduled breaks. You were able to submit a question when you registered. We will do our best to either have those answers incorporated into the presentation today, or we will answer those at the end of today's e-talk. If you have additional questions, please find the Q&A option at the bottom of your screen, and you can type in any additional questions you have. These will be reviewed and answered in the last 10 to 15 minutes of today's presentation. I also want to note that we have a couple of disclaimers. This presentation is based on sources believed to be reliable, but the AVS and authors disclaim any warranty or liability based on or relating to the contents of this e-talk. AVS and its authors do not endorse any products, processes, manufacturers, or suppliers. Nothing in this e-talk should be interpreted as implying such an endorsement. And we also have a copyright notice. The material contained in this e-talk was copied with the permission of the author of the notes, who obtained copyright releases from other materials. Since we do not own the copyright of the material in this e-talk, permission to use any part of this material must be obtained from the author. We also have some upcoming short course programs. These will be in-person programs. The first one is at our ICMC-TF 2023 conference in San Diego this May 21st through 25th. We have 8 courses taking place on various topics. These are all half-day courses running from either 8:30 a.m. to 12:30 p.m. or 1:30 p.m. to 5:30 p.m. These are going to be located at the Town and Country Hotel Resort in San Diego. Registration is available. If you'd like to check out any of these courses and register, we'd love to have you there. Also, our AVS New Mexico chapter is hosting a program at the same time, but with different courses. These will be in Albuquerque, New Mexico. They are 5 courses on various topics, May 22nd through 25th. Registration is also open for this program. If you're interested in signing up, we'd love to have you join us. We have another e-talk coming up in June on the mass production of 2D electronic medical diagnostics for home use with Christopher Muratori. These e-talks, as you've noted, are free 1-hour sessions. Registration for this is also available. And we have several upcoming topical conferences. One previously mentioned is the ICMC-TF 2023 program in San Diego in May. We also have ALD, ALE in July in Bellevue, Washington, MIOMD in August in Norman, Oklahoma. Also in August is GOX, or the Gallium Oxide Workshop, in Buffalo, New York. NAMBY 2023 is taking place in September in Madison, Wisconsin. And the AVS 69th International Symposium and Exhibition is coming up in the fall in November in Portland, Oregon. Our abstracts submission deadline is coming up on May 10th. You can find out about all these conferences and more on the AVS events calendar. There's a web link below. And if you're an AVS member, please remember to log into My AVS to access your benefits. If not, we encourage you to join us to expand your network, enhance your scientific and professional knowledge, gain opportunities to develop and practice your leadership skills, and receive discounts on various meetings, subscriptions, hotels, insurance, and more. You can find out all this at the avs.org website. If you're a student, this is also a great time to find out about student membership chapters and career services and ways to get involved with AVS. And finally, we ask that you complete an online evaluation form when you complete today's e-talk, which is on surface microscopy and microanalysis in an industrial research laboratory. Vince Smentkowski from GE Vernova Advanced Research Center is here to present for you today. Vin, welcome and thank you for coming. Please go ahead and share your screen and I'll let you take over.
Hi, I'd like to start my presentation by 2 things. One, I want to thank AVS for hosting these e-talks. The e-talks are a great way of being able to share, knowledge, which is becoming more and more important. The second things, I'd like to thank them for inviting me to present. An important point to know is I'm presenting, but the work, has been performed by a team. So I need to thank all my team members and colleagues that helped, contribute, to the content that I'll be sharing today. I see research as a team sport. You need to get over the line. And the best way of doing that in a time efficient fashion is to have the strongest team possible that could rapidly come up with an answer to a problem. As you know on the screen that I'm showing right now, where I work, we're making real devices, parts that everybody utilizes. So keep that in mind as I'm going through the presentation. Everything that I'm going to be showing has a real impact on your life. The other thing to know is, I work in an industrial organization, so I could share tidbits, but I can't go into a lot of the background. So I just want to stress the surface analysis part through today's presentation. So an outline for the presentation, I'm going to start by talking about the Research Center, the launch of the GE Vernova Advanced Research Center, and then we'll dive into the scientific talk. The first part is definition of a surface. You ask 10 people, you'll probably get 8 different answers. So just need to lay the foundation there. And as mentioned, I'm going to focus on applications of, the 3 main techniques that are used for chemical analysis: Auger Electron Spectroscopy, X-ray Photoelectron Spectroscopy, and time-of-flight secondary ion mass spectroscopy. After I go through the applications, I want to look to the future and then jump into summary conclusions and answer any questions. So as mentioned, I want to start by saying a few words about the Research Center. Our Research Center is 131 years old. It's the first industrial research lab in the United States. And an important point to know is it's also the first laboratory that had both a functional machine shop and a laboratory where people are doing research in one building. There was continuous need to improve upon, components for the research, and that was a key to enabling success. At the very beginning of the company, Thomas Edison had a quote, "I find out what the world needs, and then I proceed to invent it." And I think if you ask a lot of people at the Research Center right now, that's a similar philosophy that we have. We want to improve upon things to make devices and people's lives better. So on the right-hand side of this slide, I talk about the Research Center, and these are numbers from 2019. So at that point, we had about 1,000 scientists and engineers. Right now, that number has increased quite a bit. We generate about 3,000 patents a year. In pre-COVID, we were hosting 60,000 visitors a year. Right now, we're slowly getting back to that, but there's a lot of activity and excitement cutting across the board at our facility. So just a snippet of what all, came about because of the Research Center. The Research Center is where we come up with, the building blocks. It's the innovation engine for the company. So at the very start, we came up with the electric lamp. We then developed the first X-ray machine, and more recently, a lot of work with wind turbines. Important points to note, right now, 2/3 of the commercial flights are powered by GE's equipment engines. We're generating about 1/3 of the world's electricity. We're also enabling 16,000 medical scans every minute. And the reason we're high in all of these areas is the equipment that we're providing, and the equipment has been either designed or optimized based upon research at our facility. Another quote that people like to state when visitors are at our facility is, we're bringing research to reality. We take the idea and we turn it into a product. So a key part of doing that is understanding the materials. So to understand the materials, we have to characterize and answer questions as they come up. Within our organization, we have a vast variety of analytical equipment as shown on this page. And the bottom line is, it isn't any one technique that's going to answer all or most of the questions. Each technique has its benefits and its negative points. So as an analyst, we always need to steer people in the right direction as far as where they should go and how to most rapidly and conclusively answer the question they have at hand. The focus of today's presentation, as was mentioned earlier, is within the red box, surface analysis. And before jumping into the surface analysis, we just need to stress there's a number of things that people get out of the data that we provide. The first thing, we call it generic materials characterization, and that is, what is it? Somebody brings you a part, they need to know compositionally what it is, microstructurally what it is, what's the phase, so we provide those details. We also do materials forensics. Something unexpected happened, why? We develop methods in order to come up with a recipe for transferring a method to another facility. And we also help design the right properties for your material. And we'll show examples of all this in a minute. Another point, we help provide quality assurance and assistance through supply chain solutions. And an important point that a lot of people forget, we also provide data that are used to either develop theoretical models or validate the models. And that's of importance for, material screening. So for people that have been following what's happening within the company, in 2021, there was an announcement that GE will split into 3 public companies. GE Healthcare is now a standalone entity. They have their own research center. Right now, GE Vernova is slated to spin off at the start of 2024. And there'll be GE Aerospace. Aerospace, it's clear what their focus is, aviation related. Vernova, it's really the portfolio of the energy businesses. So we're excited to be dealing with the change. It's going to be a little bit of uncertainty over the next year or so, but we see benefits in this split. Right now, each of the three parts will have research centers that are co-located at the current facility. Okay, so now we'll jump into the scientific part of the presentation. So for many material systems, it's really the surface where the action or reactions take place. Accurate characterization, is essential. Oftentimes when people walk in with a sample, the question is, tell me what is present. As the analyst, we really need to delve further to understand what they need to know. And usually it's what do they need to change and how much do they need to change it? How, which dial and how far do they need to turn that dial? That's critical in many instances. So when you think about a surface, and when we're defining a surface, you could think of it in multiple ways. So there's film that could be on the outermost layer, and then behind the film, you have the bulk material. The film can be further classified as a thin film, and oftentimes a thin film will be sitting on top of a thicker film on the substrate. And, thin films are usually in the tens of nanometer to 1 micron range. And ultra thin films are sub-nanometer usually. And it's important to note that when we get to these really thin layers, a technique like energy dispersive spectroscopy on an SEM is not useful for providing chemical information due to the fact that you're predominantly sampling not the surface, but the interaction volume. You'll be sampling subsurface. And we'll show some examples of that in a minute. So this is a chart that compares many techniques that people think about when they're considering, analysis. Again, we're going to focus on the techniques within the red box. In this view graph, we show the sampling depth with the rectangles. If we erode to get subsurface, we could get deeper by ToF-SIMS, Auger, or XPS. And again, as we mentioned on the previous slide, many of the other techniques are sampling much deeper than what we consider to be the surface. So we always have to keep in mind, what is the thickness that's expected for the materials that are to be analyzed? And then is one technique in particular the most appropriate, or should we, pivot elsewhere? So I want to start by talking about a few examples of Auger Electron Spectroscopy. We show, photos of the Phi 700XI instrument that we have in-house. For Auger, an electron beam excites the Auger surface electrons, which are ejected and detected. All elements heavier than helium are detected. Important points to note, aside from the sampling depth, the detection limit's about a half atomic percent. And the really nice thing about Auger, as we'll show in a minute, the electron beam can be focused down very tightly. So we have a probe size of about 6 nanometers in the best working conditions. So the first example for Auger analysis, it's pretty much a substrate where these particles were present. So right away, the first thing that we do is we go in, we collect spectra. We see, there are differences. The regions 2 and 3, we're getting a spectrum that's characteristic of the silicon metal. These larger particles are iron rich. However, when we look up in this corner, it isn't just silicon. We're seeing evidence of an iron silicide. So we're seeing chemical differences, and that's nice, and that's useful, for our colleagues. However, what's really impactful are the images showing the distribution and what's actually happening. So when we map out the distribution of the chemical composition, again, in green, we're seeing the iron particles. In red, we're seeing the substrate, the silicon. And in yellow, it's very clear that we have the iron silicide. An important point to know is through the image, it's much clearer the regions of the sample that are contaminated with iron silicide. That would be difficult to get just from, the spectral analysis. With the Auger instrument, we have high energy resolution, so we could do chemical state analysis. So we see the silicon KLL peak shift when you're going from the silicon metal to the silicon silicide. So all confirmation that there's chemical differences. So this is a nice example because we show it through the spectra, the chemical state information, as well as the imaging. So this is a nice example where we're doing top-down surface analysis. A lot of times people need to know what is happening throughout the layer thickness. And, EDS analysis of a cross-section isn't able to provide the correct information. So what we could do is a series of analysis and erosion that's referred to as a depth profile. So here we're mapping the chemical composition as we step through the layer. We see the tantalum signal. It's a tantalum film on the silicon wafer. As we break through the tantalum, the silicon increases. And you note that we're getting the composition as a function of erosion time. So a lot of people would like to know what's the thickness. What we could do with the samples, take it over to the SEM, do a cross-sectional analysis, determine the layer thickness through the SEM image, and then we could calculate the erosion rate of the tantalum silicide. the important point is once we do this, we can document it. So the next time we get a sister sample, we know the erosion rate, we could optimize the data collection. What happens when we obtain samples that aren't as pristine as a, film, and we want to get the depth distribution? As you can imagine, trying to erode through a sample such as this, it's not going to be feasible. You're going to have shadowing, blocking. You wouldn't get a nice distribution. This was a fractured surface that needed to be analyzed and understood. What we were able to do is take this sample over to the Photoelectron beam instrument. We could generate, a fib, lift out from the region of importance and interest, bring it over to the Auger instrument. Within the Auger instrument, we collect the secondary electron image, and we also collect the, chemical information. So right away, we see that there are a number of different species that are distributed through this region of the sample. And that information would be hard to gather through other techniques or other perturbations. The nice thing is with a fib lift out of this size, we can do multiple regions. When we look in the second region, certain features are similar. However, towards the outermost layer, we do see some pretty significant chemical differences. So that's of importance for us to know and pass along to our colleagues. A few years ago, we were actually doing research and understanding, sensing, through butterfly wings was an item of importance. So we needed to figure out ways of trying to replicate the butterfly wings, coat similar structures, and verify the presence of the coatings that were anticipated. So many people feel that you can't do Auger analysis on soft polymeric biomaterials. However, the important point to know is that there are tricks that have been developed to enable this. Thinning the samples, similar to what we do for transmission electron microscopy, exposing the sample to low energy, low dose ions to stabilize the surface charge during the Auger analysis, applying a thin coating onto the surface to be analyzed, and or tilting while you're doing the analysis. So here, we clearly see the structure of the butterfly wing in cross section. The carbon is from the sample prep outside of the butterfly wing. We could see the nitrogen is enriched only in the region of the butterfly wing cross section. It's clear that we do have both the aluminum inner layer as well as the gold outer layer that was applied. Those are apparent in the individual images as well as the color overlay. So this is a nice example because it shows that sometimes you need to say, I don't think it's going to work, but I'm going to give it a shot. I'm going to try all the tricks in my bag to enable an analysis that we know is of importance. The second technique that I want to spend a few minutes talking about is X-ray photoelectron spectroscopy. This is a photo of the Kratos Axis Ultra DLD instrument that we have. The difference with XPS, we have an X-ray beam that excites electron emission. The electrons are ejected and detected. All elements heavier than helium are detected. It has a similar detection limit, about half atomic percent. Sampling depth is similar, but you can't focus an X-ray as tight as an electron, so the spot size is quite a bit larger. That said, as we'll show in a minute, you can collect some very useful images. An important application traditionally for XPS was the analysis of soft organic materials, especially polymers. And the nice thing about XPS, as you can see, the spectra are very simple and provide clear, intuitive results for many materials when the analysis are set up correctly. So here we could see that the specimen has carbon, nitrogen, and oxygen. Through the peak area and the application of the sensitivity factors, we get the percent of each of those elements. We could calculate the number of atoms that we would expect to be in the material, and that provides useful information. What's even more important and useful for many applications is the high energy resolution scans of the certain region, for instance, the carbon 1s region here, because what we could do is separate out the chemical functionality of the material. So from the survey scan, we get the broad view, all the elements that are present. From the high energy resolution scans of the different peaks, we get the chemical state information. And from the combination of both pieces of information, we could rule out certain chemical structures and identify which species is indeed present. So when we were talking about, sampling depth and, films, we showed this image, and this was a device that had, these features. The features were supposed to be indium tin oxide on moly, on top of a blanket silicon nitride layer, on top of glass. As you could see, delamination was occurring in certain regions, so we needed to perform analysis. The sample went to Auger for a first screen, and by Auger, we could see the delaminated region. ITO is missing from the pad, and with ITO being missing, we're seeing the moly and the nitrogen, verifying the delamination area. The group that requested this analysis really wanted to know more about the nitrogen functionality. So the sample was transferred from Auger to XPS. By XPS, we were able to go in, map the distribution here right away from the 3 elements maps from the indium tin oxide and the moly. Again, we could verify delamination occurred at that interface. But what we also get is the distribution of carbon, oxygen, silicon, and nitrogen. So here we're saying, yes, there's nitrogen that's, present in the pad as well as the film as expected. But the team that requested analysis wanted even more information. So my colleague Hong, who was doing this work, used principal component analysis of the full data set. And what she was able to do is deconvolute the nitrogen signal and image into the two components. The two components, we could clearly see the presence of the nitride and the presence of organic nitrogen functionality in the delaminated region. So the answer to the question, yes, organic nitrogen is present at the delaminated interface. When they knew and understood that, they were able to figure out what went awry in the processing. They were able to fix the process, and they were back up to producing parts with the proper yield. This is another nice example of an application of XPS. Our colleague was using barium azide, in a process, and they needed to understand what happens as the materials undergo heating. So you could predict that the barium azide is going to change to the nitride by the time you heat to about 380 degrees Celsius. And that's confirmed by these series of XPS spectral analysis performed at different temperatures. What my colleague Hong was able to do is also extract the intermediates that are forming, what temperature the intermediates are forming. And this was very useful information for the team to verify the mechanism and understand the processing conditions. We don't do a lot of analysis like this, understanding how the material changes upon heating, but it does allow us to optimize, the conditions used for materials fabrication. So the next technique I want to spend a few words talking about is time of flight secondary ion mass spectroscopy. We have an ion ToF-SIMS 5 instrument. The difference here is pulsed ion beam strikes the sample, surface species are ejected and detected. We get a full mass spectrum at every volume element. Nice features of ToF-SIMS. We have very high chemical sensitivity, part per million, part per billion for most species. We collect information related to hydrogen. We get isotopic information. And as I'll show in a few slides, we could also obtain molecular information, which is critical of certain processes. By ToF-SIMS, we've been able to erode as deep as about 40 microns. And when we do a depth profile, we get a 3D image, as I'll show in a minute. So this is an old example. It was a device that was being fabricated. It's a gold pad. And the question at the moment was, is copper present in this small region? The sample was analyzed using a variety of techniques. They couldn't conclusively say if it was or wasn't present. When the sample came to me, within a few minutes, not only was I able to show that yes, copper is present, but I was able to show that it's distributed pretty much uniformly throughout the gold pad. Although we don't have sensitivity factors for copper on gold, based upon the other techniques that were used and weren't successful, we know that the amount of copper in this example was less than about 900 parts per billion. So it's a nice example of showing when you would start with the technique to answer, is something present in low amounts? The other advantage of SIMS, since we collect the full mass spectrum at every volume element, oftentimes we find unexpected surprises. This is another example, and I feel that the display right now, you can't visually see it easily, but there were dark regions on this sample and also light areas. The colleague that brought me the specimen asked to collect spectra in those different regions. What I did was set up to do stage rastering. So I rastered over about an 8mm by 8mm area. And right away, I could see chemically what was different between the dark areas and the lighter areas. In the dark areas, we're seeing exactly what we're supposed to with the right distribution, chrome and nickel. In the areas that had the lighter color, we're finding polydimethylsiloxane, PDMS. So at first the colleague was in disbelief, but like, that can't be the reason. But after talking a little bit further, we were actually able to identify the source of the PDMS, identify a protocol for preventing PDMS contamination, and the issue has not reappeared. So within the one business unit, we have thin film deposition equipment. This apparatus, had 4 target bays. 2 of the target bays always have, targets that are being used in them. 2 other target bays are typically empty. There was the desire to possibly use these as storage areas. There was the realization that they could become contaminated. So our colleague put glass into slots 1 and 2. They deposited about 100 microns of ITO from targets 3 and 4. The glass was removed. They started by EDS analysis, and the EDS said there wasn't any ITO present. They brought the samples to me, and by ToF-SIMS, I was able to show, yes, we do have indium, and what I'm showing here is the tin. There's certain areas are more consistent. There's some variation. The composition that we were detecting is indicative of ITO contaminants. So this is one of the many examples we have where the interaction volume of EDS, you're pretty much sampling right through the layer of interest and sampling the underlying material. So it's very important, especially when I'm looking at low-level species that may be present at low concentrations, to select the technique that has the correct sampling depth and could provide the most robust answer. When we were talking about Auger, I showed an example where there were metal layers placed onto the butterfly wing. That same colleague was treating the butterfly wings with porphyrins. He came to me and he said, can you detect, this porphyrin on a butterfly wing? So my first answer was what I would usually say. The best way of understanding if we could do that would be give me the uncoated butterfly wing and give me, the material that you're functionalizing it with. I'll get the fingerprint spectra and we could then decide if it's a viable path forward. So the nice thing about this porphyrin is there are high mass molecular peaks that we're obtaining. When we looked at the untreated butterfly wing, there weren't any peaks within this mass range. So he was able to expose the butterfly wing to the porphyrin. We were able to image the distribution of the porphyrin and show that there's enrichment at the outer edges of the scales. The important point to note, the edges of the scales are hydrophilic, and the hydrophilic nature stems from the large quantities of polysaccharides present at the internal structure of the scale, which are exposed, at the edges. So we were able to get nice molecular chemical information to provide insight as far as the functionality, of the butterfly wing in this instance. So when we were talking about Auger analysis, we mentioned depth profiling, and depth profiling through inorganic species has been possible in traditional monoatomic sources such as argon, cesium, and oxygen, have been very useful for ToF-SIMS as well, and other varieties of SIMS. But the problem is you expose a biological material to these ion sources, you have decomposition. That was realized early on. So a number of research groups optimized cluster ion sources. The first cluster ion source was SF6, which was developed really for molecular spectroscopy. Then there was a realization we want to focus the beam. So the gold and bismuth sources came about. And then to optimize depth profiling, C60, cornene, and argon cluster sources, became available. In this example, we had two different species that were mixed together for an organic solar cell. My colleague needed to know the composition throughout the thickness. When we expose this to a monoatomic ion beam, we pretty much got carbon. Here we could see the molecular signatures throughout the thickness of the layer, and we're seeing some enrichment at the interface. At the interface, we're also seeing sodium. A big surprise was the nitrogen functionality at the interface. So a key learning in this instance was the nitrogen functionality. With SIMS, we collect the image at every depth of a depth profile. We have a ton of data that are available. I've been working with a number of colleagues on multivariate statistical analysis, where we pretty much boil the entire data set into a few components. And the nice thing about the multivariate analysis is we could identify, number one, the layers that are present through the component. And, for each of the layers in this instance, we have a full mass spectrum describing what's happening, not just one peak. If we just focus on the interface in this example, we could see that there are slight differences in the distribution of the cadmium, oxygen, and beryllium. And that was important. That would have been hard to find and extract from just manual univariate analysis. So advanced data analysis tools are important. What I want to end with as far as an example, we mentioned using FIB to prepare for Auger. We had an example where we sent a section of a lithium-ion battery for in situ SIMS FIB. Here we have, the FIB slice. And without exposing the FIB slice to ambient, we were able to map the distribution of the species that are present. And as mentioned, for the 3D depth profile, we were able to take the full measured data set, run multivariate analysis, and get the distribution associated with the different factors. And factors here have a molecular signature, so more useful information than we could get with just manual analysis. Running low on time, so I want to jump to the future of surface analysis. Everybody wants to have a tighter focus. So next generation of instruments, they'll have smaller analytical spot sizes, higher detection efficiency, faster analysis, higher resolution, higher mass range, less beam damage, more advanced data analysis algorithms such as multivariate analysis. However, the important point is we're still going to need skilled operators to properly interpret the data sets. Hybrid instrumentation, such as FIB, ToF-SIMS, AFM ToF-SIMS, MS ToF-SIMS, in situ FIB Auger, those are all going to be becoming more and more important. So I just want to close by saying, characterization is really key to understand the material's behavior. Oftentimes, multiple techniques are needed to analyze the material. When an analyst gets a sample, they shouldn't just tell the colleague, you have carbon, nitrogen, and oxygen. We have to help and we have to provide them the input as far as what the data means. The bottom line is we need to tell them what process needs to change and how much. In-house, we have a variety of analytical equipment that can be used to answer the key questions. The questions are becoming more challenging, smaller dimensions, low concentration of species. No one technique will answer all those questions. Again, I'm presenting the work. A number of the analysis were performed by my colleagues. I list the teams here. I have a whole slew of external collaborators, which I must thank as well. I'd like to thank all of you for attending. Feel free to reach out to me if you have any comments or questions. An important point to know is we are hiring. So if people are interested or know of people that are looking, they could find us online or reach out to me. So while entertaining questions, I just want to show the history of characterization innovation within the Research Center. This is a slide that we put together a number of years ago. And I think it's just exciting to revisit periodically. Again, thank you for your time, and I'm willing to entertain any questions you may have.
Great. Thank you very much, Vin. And thank you everybody for joining us today on the AVS e-talk on surface microscopy and microanalysis in an industrial research laboratory. Thank you, Vin, for preparing and presenting all the information. We do have a few questions that came in prior to when you were registering. So I'd like to read one of those for you, Vin, to field right now, if you could. Do you see the use of AES growing or shrinking for industrial materials and R&D?
That's always a good question. So Auger is actually being used more heavily than people see. The important point to note is the semiconducting firms use it very heavily. However, they cannot share what they're learning. So there are many Auger analysts out there. However, they're not presenting. They're coming to meetings to soak up information. As far as what do I envision, I would envision more hybridization of Auger instrumentation, and that's starting to happen. So I would say it'll probably stay kind of steady state-ish, maybe a slight increase. I don't think it's going to go away.
All right, thank you very much. Again, I just want to remind you, you can use the Q&A feature at the bottom of your screen to type in any questions you have, but I do have another one here for you, Vin. In the corporate research environment, what importance does participation at technical symposia have for a development, and is participation in these symposia perceived as beneficial?
So the way I see it, if you attend a symposium, you're going to learn. Most useful information always comes from the side discussions, finding out what people have tried that didn't work, finding out something novel that they're not publishing and presenting, and especially for the people in industry, knowing, hey, my colleague has this issue. Who within the community do you reach out to for input, suggestions, or advice? So I think it's most of that where the industrial sector benefits. I mean, we learn from hearing what the people are presenting, and that's the foundation. As far as management, every manager is different. When you've come back with critical information that you've shared with your colleagues, usually they will be supportive, of attending. As far as being actively involved, that's really up to the individual. It's something that I always recommend and suggest. You really have to be your own advocate there.
All right, and we've got another minute or so. I got a couple more quick questions. How do you solve analysis of thin or very thin films?
That's actually one slide that I jumped over. So again, you have to think through what is the layer structure, how thick or thin is it? There are times where you could optimize a depth profile. There are times that you could do, fib prep and then analysis. However, something that Nick Winograd's colleagues did about 25 years ago was a web preparation and certain instrument manufacturers are now building this into their data collection protocol. So what you do is you generate a bevel into your sample, and you can do that very rapidly. Once you have that bevel, you could map the distribution of the species, as I'm shown on the right-hand side here. And then once you have the map, you can generate an area line scan. And the nice thing, especially when you think about SIMS, usually you're selecting, do I look at the positive or the negative ion fraction? And it's 1 per region. Here, after you have the wedge prep, you could do a positive ion analysis, and then within the same exact area, you could do the negative ion analysis. So it's not, every sample is different. And as an analyst, you always have to think, what's the right starting technique? What's the right approach? And then be ready to pivot based upon what you learn.
All right, and one final question. Can you comment on ToF-SIMS used as dynamic SIMS and non-ToF-SIMS instruments, i.e. quadrupole, magnetic, in-static SIMS? Do I need to break that out, or are you good?
No, I think I got it.
Okay.
So the main benefit of ToF-SIMS is the full mass spectrum at every volume element. What I often find are surprises. And when I say surprises, it's unexpected things at the interface. If you were to be doing a depth profile using a dynamic SIMS instrument, for instance, you have to select which species you're going to analyze for at the beginning. So you're already kind of biasing, what you're going to be learning. When you have all the data, as mentioned, you often find unexpected surprises. I think that probably fully answers the question. With ToF-SIMS compared to dynamic SIMS for depth profiling, you may not have as high a chemical sensitivity for certain species, but I haven't run into a situation where we weren't able to get useful information.
All right, thank you very much, Vin. I think that will cover our questions for now. I don't see any other questions in the Q&A box. I'm just going to do a few closing slides, and thank you for presenting and preparing the material today. And thank you everyone for joining us for the AVS e-talk on surface microscopy and microanalysis in an industrial research laboratory. I do want to remind you that we have some upcoming short course programs. One is ICMC-TF 2023 in San Diego, California. We have 8 half-day courses coming up. We also have our AVS New Mexico chapter short course program in Albuquerque, New Mexico, with 5 additional short courses. These are overlapping timeframes, but maybe you're in a certain area that allows you to travel to either one of those. So please check those out. We do have another e-talk coming up in June on mass production of 2D electronic medical diagnostics for home use. Registration is open. This is free 1-hour event similar to today. And we have several upcoming conferences that you can find on the AVS events calendar between now and fall. We have ICMC-TF, ALD, ALE, MIOMD, GOX, NAMBI, and the AVS 69th International Symposium and Exhibition. I know that's a lot of acronyms, but hopefully some of you know what all these mean. If not, please check them out on the AVS events calendar. They are all taking place in person and in various locations. If you're not a member, we do encourage you to join. We are a great family to become part of. We have a very broad range of members in various fields of interest. So please check us out. You can go to avs.org and find out more about us, including having access to our technical library and publications and journals. For students, we have student chapters, career services, and more. And finally, as you're logging out, you should see the online evaluation form. If not, it will also be emailed to you. And thank you again, Vin, and thank you everyone for joining us. And we hope you enjoy the rest of your day. Thank you. Bye.